Okay, so this is the second part of the same video. So we just got done talking about how to find expected counts for one variable in a categorical situation, chi-squared goodness of fit test. So there we go. Where does that bring us? So if we've got those expected counts, then we should be able to actually find the chi-squared test statistic. So remember, assuming that the null hypothesis is true, this is all based on the idea that the expected values are what we think they are. If chi-squared equals 0, then there's no difference from what was expected. So we would put those in there. If our chi-squared value is large, then that means our result is a lot different from what we expected, and that could possibly be evidence against that null hypothesis. So remember, observed minus expected squared divided by expected, and this is on your formula sheet. Okay, so if I'm getting very small differences here, I'm getting an answer very close to what I expected. If I'm getting a large answer for my chi-squared value, I'm getting a very different scenario than what I expected. So I'm concerned. Why didn't I get what I thought I was going to get? All right, so remember that we did this problem with the red, orange, yellow, green, and purple Skittles. So down here in the problem, we said the observed values were what came out of the bag, and the expected values, since we had 150, that 150 spread evenly, uniformly across those 5 categories would cause us to expect to get 30 in each. So I would sub all these values in into my equation, 23 minus 30 squared over 30, and 28 minus 30 squared over 30, etc. For each of those values, here's the purple, 33 minus 30 squared over 30 at the end. Every observed value minus its expected value squared, then divided by those expected values. The sum tells me after I find each of those, I add them together. Now, I just did this in my TI Inspire. You can kind of see down here in the corner, just did the whole step at once. I got a chi-squared value of 5.0667. And you should probably use at least 3 decimal places, if not 4, on these values. Probably no less than 3 to be on the safe side. All right, so here's our other example. These were the Reese's Pieces. We, in the bag, got 36, 15, and 16. That was 67, with expected values of 33.5 and then 16.75. So again, the chi-squared value would be the observed number minus the expected number squared all over that expected number. And I did this again in my calculator, and I ended up with 0.402 and some change there. And I went ahead and put 3 decimal places on that one. This chi-squared value is quite small compared to the other one. So remember, we got 5 here, and I got something really close to 0 here. So the results from the Skittles are more different from what I expected than the results from the Reese's Pieces are. Okay, so what does that mean? So we can find the expected counts. We're doing some NPs there, just like we did back in chapters, the previous chapters. And the chi-squared test statistic, we can compute that by hand. We're using our formula, plug and chug. Now what? So the chi-squared distribution looks like this thing I've got over here on the right, and it's specified by degrees of freedom, much like the t distribution is. So just like t, as the degrees of freedom changes, so does the what we see with the distribution. So the chi-squared distribution, the total area under the curve is equal to 1. So we can use this as a probability distribution. So we can associate the areas under the curve to the probability of getting a value in that region of the curve. The other thing is that the curve begins at 0 down here. So the very smallest that your chi-squared value can be is 0. And it increases. So each of these, they increase to a peak, and then they stretch out to the right. Okay, so they increase to a peak and then approach that axis from there. But again, the smallest can be 0. 0 means what you see is exactly what you thought you were going to get. And then each time you're looking at the chi-squared distribution, it is going to be skewed to the right. However, as your degrees of freedom increases, it starts to look more symmetrical, and eventually it looks approximately normal. Okay, but the degrees of freedom is going to be a much more unlikely to have a large degrees of freedom. Most often we have a pretty small degrees of freedom in these problems. I'm going to explain why here in a second. Okay, so again, the idea is that the larger the degrees of freedom, the more spread out the graph is, the less of a high peak on the left side tailing out to the right. It becomes more and more symmetrical the higher that degrees of freedom is. So the degrees of freedom for a situation where you have one variable for one population of interest, instead of being n minus 1, like it was in chapters previous to this when we talked about t-tests, the degrees of freedom is k minus 1, where k is the number of categories of the variable. Okay, so the number of categories in this case, so when I look at my Skittles, I've got 1, 2, 3, 4, 5 different categories. That means my degrees of freedom would be 4. And then with the 1, 2, 3 different colors, 3 different categories of Reese's Pieces, that gives me a degrees of freedom of 2. All right, so I'm going to go back really quick to that picture where we talked about this degrees of freedom 15. That would mean you would have to do a survey or observe some characteristic of a population where you had 15 different measurable categories there. So the likelihood of getting up to a chi-squared distribution that actually is approximately normal is not very likely. Most of the time when you think chi-squared, you need to think, this is going to be skewed to the right. Okay, now, when we are doing a chi-squared test, we're going to be doing our phantoms process again. So when we get to phantoms, eventually we're going to need to find that test statistic. And so the test statistic is going to be our chi-squared value. And we know how to calculate that by hand now. Good job, us. But we also are going to need to obtain that p-value, obtain the p-value. We're going to primarily be doing that in our calculator. If you go into your stat test menu in the TI Inspire, you'll notice there's one that says chi-squared GOF. That stands for chi-squared goodness of fit test. And then the other one is the chi-squared two-way test, which we will use for tests for homogeneity and independence. Now over here, when I actually run that test, so here's with the Skittles problem here, observed values, expected values, I run that goodness of fit test, you can see the chi-squared value of 5.066, which we did calculate by hand earlier and got the same number. And you'll notice there it's got a p-value of 0.281, so about a 28.1% chance of getting results like ours if that hypothesized value, that percentage was true. Those percentages were true in that null hypothesis. Okay, so the p-value there, what that represents is in your chi-squared distribution, what we're always talking about is the area that's under the curve from your chi-squared value. So the boundary mark, that's your test statistic, that's your chi-squared to the right in this right skewed distribution. Yes, I noticed that the one that I pulled off the internet as a free picture here, that's not the same as any of our examples, but that's the idea. That's the p-value is that area under the curve. So if you wanted to find this by hand, you could, just like you could find the area under a normal distribution or the area under a t-distribution. We know that our chi-squared value is 5.0667 and the degrees of freedom is 4. So if I would go into my distribution menu, remember we have norm CDF tells us the area under a normal curve. T-CDF gives us the area under the curve in a t-distribution, and chi-squared CDF would give us the ability to calculate this little business over here. So to do that, I would go from my chi-squared value, my boundary, and in this case up to infinity, and my degrees of freedom. Notice we end up with 0.280522. That is our p-value, okay? And that is the same p-value that we got when we use the calculator command to do this. There also is that 0.28. So we can get the chi-squared value by hand. We can get the p-value using our technology, or we can pull them both out of the spreadsheet. Okay, so here's what you need to be able to do today. This is lesson 1. Here's your things you get. I need to be for you to be able to say, I can describe the shape of a chi-squared distribution and explain what happens to the shape as degrees of freedom increases. So basically, you need to know chi-squared is a skewed right distribution, and that x-axis starts at 0 and could theoretically go up very, very, very high. But from 0 is where it starts, and it's skewed to the right. And as the degrees of freedom increases, this becomes less skewed right and more symmetric, and theoretically, eventually approximately normal if you had a massive number of categories. Because remember, degrees of freedom is categories -1 now instead of sample size -1. The other thing is that we're for one categorical variable from one population. We're talking about a goodness of fit test here. You need to be able to calculate the expected values for each category. So you're going to use those n times p calculations, but you're going to have multiple ones of those. You're going to have P1 and P2 and P3 and P4 and P5. Those are your expected values. You need to be able to compute the value of the chi-squared test statistic. So you need to be able to use that formula, which is on your formula sheet, that observed minus expected divided by expected. Squaring that numerator and then adding all those pieces together. Okay, so you know that chi-squared value. And then you need to be able to determine the degrees of freedom for chi-squared. So degrees of freedom, remember that is k minus 1, where k is the number of categories in this case. Okay, so what's coming up next in the our next lesson is we're actually going to use the phantoms process that we've been using in the last couple of chapters, this hypothesis testing idea, and we're going to actually do a goodness of fit test for chi-squared. Okay, there are some things that are going to be a little different. The hypotheses look a little different. We might be expressing them with variables. We may be expressing them in words. Assumptions and conditions are a little bit different. So chi-squared tests are going to have different assumptions than we had for either proportions or means. We're going to have to check those. The name and the test statistic is now a chi-squared test, and we have a chi-squared value instead of a z or a t, so that's a little bit different. Things that are basically the same, you're still defining parameters. So anytime you use a variable p, you need to say it's the true proportion of your population in the context of the problem. You are still going to be using our calculator to do almost all the heavy lifting in terms of mathematics. You need to know how those formulas work and how those areas are calculated, those p-values are calculated, but most of the time our calculator is going to spit those numbers back for us. Interpreting p-values is exactly the same. So you're going to be comparing your p-value from the calculator or from that chi-squared CDF command. You're going to be taking that value and comparing it against alpha and saying, ooh, the p-value is less than alpha, so I reject the null hypothesis. Or the p-value is greater than alpha, so I fail to reject the null hypothesis. All of that is basically the same. Okay, so when you watch the next video, we're going to put all of these pieces together and actually run the hypothesis test. But for today, again, you need to be able to talk about shape. You need to be able to calculate those expected values. You need to be able to compute the value of an actual chi-squared test statistic. You may need to go back in the video and watch that again. And you need to be able to determine the degrees of freedom for that chi-squared test. Thank you very much.